On September 11th, 2025, as the planet dozes, a hobbyist from Ukraine spots something that massive observatory arrays overlook entirely. A comet flaring up with the luminosity of 10,000 generating planets. Its tail extending broader than 5 complete moons placed side by side. Meet Comet Swan. 400 times more radiant and twice as vast in the heavens as the famed interstellar traveler 2I/Borisov. Wait, no, the renowned 2I/Atlas. Still, it can be detected using just ordinary binoculars. In an unprecedented twist, a home-based observer has surpassed elite global skywatchers, reshaping the guidelines for unearthing celestial wonders. So, how did professionals miss a dazzling display right under their noses? And what happens when the most luminous comet in ages outshines an extraterrestrial wanderer that's barreling toward a potential 47-day impact? These revelations challenge our understanding of the solar system's hidden secrets. Yet the real marvel lies ahead. Vladimir Bezugi doesn't let time dictate his evening routines. Unlike many pros who rely on robotic scans to comb the stars, he hunches over an old laptop, poring over hydrogen visuals relayed from the SOHO probe. Shortly past midnight UTC on September 11th, 2025, a subtle, drifting smudge grabbed his attention in the Virgo region. A teal vapor intensifying in the newest SOHO subtraction frames. Bezugi, seasoned from over 20 comet detections, hesitated. This wasn't any equipment malfunction. Image after image, the haze sharpened, expanding farther than any prior record in his files. In moments, he executed his tailored algorithms, marked the oddity, and shared marked-up captures on the Comet ML forum and Telegram's SOHO Monitor group. By 1:30 Universal Time Coordinated, he dismissed all typical false positives and submitted an official alert to the Minor Planet Center. The object's glow, hovering around magnitude 7, made it detectable for folks equipped with simple 50mm binoculars. Such ease of access is virtually unknown in today's comet pursuits, where finds usually hide beyond amateur gear's grasp. Hours later, Martin Mosek's crew at the Czech Fram Observatory verified it via terrestrial photos, sparking a worldwide frenzy of shared positions and brightness data spanning time zones. Bezugli's method, sifting through fresh SOHO subtraction charts for shifting hydrogen signatures, had just upended the norms. Amid a realm ruled by multi-billion-dollar instruments, one dedicated hobbyist's sharp gaze had unveiled a wonder concealed in full view. The era of open-access exploration wasn't mere speculation anymore. It was a blazing comet streaking overhead, within reach for anyone who pinpointed its spot. 12 hours post-find, experts were already plotting its path meticulously. The stats are mind-blowing. By September 12, 2025, Swan hurtles by the Sun at a mere 0.5 astronomical units, roughly 75 million kilometers, the span from our planet to Venus. Then, 5 weeks on, it veers even nearer to Earth, grazing within 0.26 Australian dollars, or 39 million kilometers, come October 19th. That's deeper into the inner solar system than Mercury's path, near enough that the tail spans 5 degrees across the view, matching the span of 10 moons aligned tip to tip. But the route tells just half the tale. The comet's vapor ejections, triggered by solar rays striking pristine ices, are projected to unleash energy at almost 10,000 gigawatts. No mistake there. To put it in perspective, humanity's total output from every facility at peak barely equals that surge. In sheer force, Swan acts like a drifting powerhouse, expelling more vigor into the void than all urban centers worldwide. These figures go beyond theory. They prime us for an extraordinary show. A comet vivid enough for casual binocular views, cruising so swiftly that its chart placement alters nightly. For sky experts, the approach to perihelion isn't simply a date. It's an urgent bid to log every detail prior to the tightest pass and the unfolding of this stellar drama sequel. Few will ever glimpse 2I/Atlas, even through premium binoculars. Its sheen clocks in at magnitude 13.3, a figure that seems vague until you realize it renders the comet some 360 times dimmer than Swan. That's precision, not approximation. On that scale, each interval of 5 magnitudes signals a 100-fold brightness drop. Thus, as Swan gleams at the edge of naked eye vision, Atlas lurks in obscurity, accessible only to pros or hardcore enthusiasts with high-end scopes. The scale difference hits hard too. Atlas's coma, the hazy envelope encircling its nucleus, covers just a handful of arcseconds, scarcely more than a far-off point of light via eyepiece. Swan, however, sprawls over entire degrees of the celestial dome. For the average person, Atlas stays a mere entry in logs, a pursuit for specialists and gear-heavy aficionados. The barriers stem not from intent, but from optics and remoteness. This one's reserved for the observatory inner circle. Velocity by itself distinguishes 2I/Atlas from any comet in recent history. Traveling at 58 kilometers per second, it covers the span between New York and London in less than 2 minutes. Unlike objects drifting within our solar system, this one qualifies as a genuine interstellar voyager, tracing a hyperbolic trajectory that ensures it escapes the sun's pull forever. When Atlas reached its perihelion 36 astronomical units away, roughly 203 million kilometers from the sun, teams at the European Southern Observatory directed the Very Large Telescope at its dim nucleus. The resulting spectra uncovered an unanticipated composition, a mix heavy on carbon dioxide, outnumbering water vapor by an 8:1 margin. Even more startling were the unmistakable traces of nickel vapor, a substance seldom spotted in comets and virtually never in such quantities. Observations verified by separate facilities suggest origins distant from our own solar neighborhood. For experts in planetary science, the subtle light of Atlas hides valuable insights into the chemical makeup of alien star systems. Among professionals, the buzz centers not on the visual display, but on the enigmas embedded within this swift, otherworldly guest. October 8th marks a stark divide in the heavens. Both Swan and Atlas retreat sunward, falling under 20 degrees of solar elongation, the threshold below which no earthbound telescope can observe them without risk. From October 8th through 18, a span of 11 days, observatories worldwide lose their view entirely. Sophisticated equipment proves useless against the overwhelming solar brightness. No photos, no spectral analysis, no ongoing monitoring. This observational void hits at the most inopportune time. Precisely when Swan draws nearer to Earth and Atlas hurtles toward its solar encounter, the bursts of activity, the outflows, the unfolding developments, all go unseen if anything noteworthy unfolds. The schedule feels unforgiving. The 47-day interval separating Swan's perihelion from Atlas's own high point gets bisected by this unseen barrier. Researchers model trajectories, review almanacs, and exchange worried predictions on online boards, yet the quiet persists. The cosmos guards its mysteries until the comet's return, creating a void in the data that no tech can bridge. Uncertainty embeds itself in Swan's very path. At the Minor Planet Center, experts match the data to a cycle of 1,400 years, implying a return within human history's timeline. NASA's JPL team, applying alternate models and incorporating imprecise prediscovery snapshots over a broader span, extends it to an immense 20,000 years. This divide, nearly 19,000 years wide, stems not from competition, but from the inherent constraints of limited observations over mere weeks before the sun's interference. Both estimates remain tentative. Their validity hinges on confidence in dim detections from stereo A or the accuracy of sparse terrestrial readings. As the interruption lingers, variant trajectories and statistical runs accumulate on agency computers. Still, the blank spot endures. Far beyond theory, this involves enthusiasts peering through field glasses and specialists at elite facilities in a worldwide push to clarify the facts. Fresh updates pour in from Australia, Europe, and the Americas. Every datum feeds into live sky databases. Each photo gets vetted instantly on shared platforms. Though the sun blocks visual scopes, the dialogue flows uninterrupted. In the midst, Comet Leonard enters the fray, its tail glowing to magnitude 4. Over several weeks, the night sky transforms into a communal experiment, with spotters from home setups to labs joining forces. Lingering puzzles, Swan's duration of absence, its concealed traits, the brevity or vastness of its loop, propel the narrative. Here, science emerges as an ongoing endeavor, driven by collective input and open questions. On September 11, 2025, Vladimir Bezuki spotted a comet via NASA's SOHO/SWAN tool, 400 times more luminous and 200 times bigger across the sky than the interstellar 2I/Borisov or C/2019 Y4 Atlas. Backed by the Czech Academy of Sciences and released brightness figures, Swan's tail stretched 2 to 5 degrees with a top magnitude of 6.2, rendering it binocular-friendly, whereas 2I/Borisov, the quickest interstellar object logged at 58 kilometers per second, stayed 360 times dimmer and required prograde scopes. Each faded behind the sun for 10 days near their solar minima, carving out a vital observational hole. The rift between JPL and the Minor Planet Center on Swan's period, from 1,400 to beyond 20,000 years, lingers unsettled. Even with international collaboration and instant monitoring, queries endure about how a magnitude 6 body slipped past prior scans. This campaign saw hobbyists and pros united as rare alignments unfolded in luminosity, size, and enigma, verified by facilities spanning 3 continents.